Okay, so this second video on the chain rule follows on the one we just did where we introduced the chain rule. We looked at a couple of basic examples, and in this video we're going to look at a couple more examples where we make use of the chain rule. Okay, so here's our first example. So in the previous video, we broke things down using the Leibniz notation and introducing intermediate variables. Let me show you the other way you can do it if you want to kind of work with function notation and sort of this prime notation. So we can think of this as g of h of x, where g of x is, so that's the outside function. The outside function here is the exponential function. The inside function is the sine function, right? I'm taking sine and I'm plugging into the exponential function to get f of x. So the chain rule says that the derivative of this composition is the derivative of the outside evaluated at the inside, and then I multiply by the derivative of the inside. So we know that g prime of x is, well, the exponential function is its own derivative, so we get e to the x. H prime of x, we have cos x. So we can actually plug things in here. So g prime is e to the x, but I have to evaluate at h, right? So I have to take h of x, which is sine x, and I've got to plug it in to e to the x. So that gives me e to the sine x, and then I multiply by h prime, which is cos x. And by the way, this is a general pattern you'll notice with exponentials. If you have e to some function and you want to take the derivative, notice that the way you take the derivative of e to some function is you keep that same exponential term and then you multiply by the derivative of the exponent. Okay, so you can try a few more examples like that, and you'll find that that's always the way it goes. Now, let's look at this next one. We'll do it kind of, we'll do it blindly first, and then we'll try to be a little bit more smart about things. So in this case, I can think of this. So if this is, let's do the Leibniz notation this time. So let's call this thing y. Okay. So y is equal to the natural log of u, where u is equal to x to the 9. So dy du, let's remember the derivative of the natural log is 1 over u, and du dx, I did power rule, I get 9x to the 8th. So that means that if I want dy dx, I should do dy du times du dx. So I should get 1 over u times 9x to the 8th, but remember we don't want to leave it like that. We got to put u back in terms of x. So 1 over x to the 9 times 9x to the 8th. Okay? Alright, and then you could simplify from there if you wanted to. But note also, if you want to be smart about things, remember one of our rules for logarithms is if I have an exponent, I can take that exponent and I can bring it out front. So what do I get? G of x, I can write g of x as 9 times the natural log of x. And so you know what? I didn't even need chain rule because all I actually need is the constant rule. G prime is going to be 9 times the derivative of the natural log, which is 1 over x. And notice that if you do simplify our earlier answer, that's exactly what you get. Once you've got the chain rule, it's kind of it's a very blunt hammer that you'll be tempted to kind of swing at almost every problem. But sometimes with a little bit of clever rewriting, you can give yourself a much easier problem that doesn't require the chain rule. Something to keep an eye on. Now, let's look at exponential functions, right? So let's say we want to calculate the derivative of a general exponential function here. Okay, a is some positive real number. We want to know what is f prime of x, right? Now, we went over in class the fact that we really like the natural exponential function because it's its own derivative. It has this very simple derivative. What happens if you change to a different base? Is the derivative quite as easy? Well, almost, but not quite. So what we have to do is we make an observation. One of the things we do is we say, I don't know anything about exponents to other bases, but I know everything I need to know about the natural exponential, everything I need to know about the natural log. And I also know that the natural exponential and the natural log, those are inverses of each other. So I can do this. A to the x is the same thing if I take the natural log of a to the x and then I take that and I plug it into the exponential function, right? E and ln, they're inverses of each other, so I haven't done anything. Those are actually equal. And why is this useful? This is useful because, as we mentioned in the last example, that exponent, it can come down in front. And so I can write this as e to the x times the natural log of a. Well, that means that the derivative of a to the x is the same thing as the derivative of e to x times the natural log of a, right? And the natural log of a is just a number. It's a constant, right? This is just a constant times x in the exponent. And chain rule says, and we just did, we mentioned in this previous example, right, that when you want to take the derivative of e to some function, you take the same thing and then you multiply by the derivative of that function. So what you get here is you get that same exponential, and then I multiply by the derivative of the exponent. Okay? That's where the chain rule comes into the picture. All right. But let's simplify. Remember that e to the x log a, that was just a to the x. That was a fancy way of writing a to the x. And if I take the derivative of x times log a, remembering that log a is a constant, the derivative of x is just 1. So I get the natural log of a. Right? So this is why we like the natural exponential, because the natural log of e, of course, is just 1. We don't get this constant multiple. When you take the derivative of exponential functions to other bases, you get this extra constant coming out every time you take the derivative, and that constant can get a little bit annoying, so we like to work with e to the x for that reason. Okay, here's a similar trick that lets you extend the power rule, right? So we showed that the derivative of x to the n, so we have this power rule, right? But really, we've only proved this when n is equal to, 1, 2, 3. When n is a natural number, we've shown that the power rule works when n is a natural number. I claimed back in the power rule video that it works for any real number, but I didn't give you any evidence to back up this claim. So how can I convince you that this is true? So let f of x equal x to the a, where a could be any real number. Well, what I can do is I can do the same kind of trick here. F of x is equal to e to the log of x to the a. And again, properties of the natural log, let me take that a and bring it down in front. Okay? E to the a times the natural log of x. So what's f prime of x? Well, chain rule says take that same exponential, e to the a log x, multiply by the derivative of what's in the exponent. Okay? A is just a constant, so we just have to worry about the derivative of the natural log, which is 1 over x. So we get, what do we get? We get, well, first of all, remember what this is. This was just x to the a, and then we get a over x. Okay, but let's simplify that. Let's put that a out front. X to the a, I divide by x, Well, laws of exponents say if I divide by x, I should subtract 1 from the exponent, a minus 1, and we've done our job. Now, you have to be a little bit careful here. You could reasonably object that the argument I've given here only works if x is positive, and I should give you a separate argument if x is negative, right? Because the natural log of negative numbers isn't defined. The same issue would arise at 0. But this gives you kind of a better idea of why we should expect this power rule to work no matter what the exponent happens to be. Okay, now we'll end with one kind of tricky example. A function to the power of another function, x to the power of x. How do you calculate the derivative of this thing, right? I can't treat it as an exponential function because an exponential function has a constant base. I can't treat it as a power function because a power function has a constant exponent. What do? Well, I use this same trick as last time. X to the x is equal to e to the log of x to the x. Okay, which is, if I bring that x out front, e to the x log x. Alright, so that means that f prime of x is the derivative of e to the x log x. Oops. And as before, the exponential function sticks around, e to the x log x, and we multiply by the derivative of the exponent. So now instead of a power there, I only have a product, right? Logs are nice, they turn powers into products. Now this first part here, that's still my x to the x, and what do I get for this derivative? I get 1 times the natural log of x when I take the derivative of x, plus x times 1 over x, right? And of course I could simplify that if I want to. I get x to the x times the log of x plus 1 for my derivative. Okay, so that's all we'll say for the chain rule. Now in the next few videos after this, we're going to look at logarithmic differentiation, we're going to look at implicit differentiation, which are two extensions of the chain rule to more general situations where you have equations involving both x and y.